So now we are going to talk about the actual method, the annihilator method, to solve these differential equations. So the example one that I'm going to look at is y triple prime minus 3y prime plus 4y is x e to the 2x. Notice, by the way, there's sort of a y prime term missing. There's a 0 times y prime that we could stick in there if we wanted. Okay, I want to think about this in terms of a differentiator operator. So I'm taking some differential operator and I'm applying it to y, and I'm getting the function x e to the 2x. Okay, and what is that differential operator? It's going to be d cubed minus 3d squared plus 4. Okay, so thinking back to the previous video, whatever my function is, I'm applying that to it, and that means I'm taking the third derivative, and then I subtract 3 times the second derivative, and then I multiply 4 by the function and add them all together. When I do that with this particular function y, if it's a solution of this equation, I get x e to the 2x. That's the claim that this equation is making, and I want to find a y that actually solves this equation. Ideally, I'd like to find all of the y that solve this equation. Okay, so that's my goal. In order to do that, I'm going to use a certain fact. Okay, and I'm going to use what's called an annihilator. So I will use how do you spell annihilator? There's got to be an N in there. Let's see if I can erase. Yeah. Here, you know what? I'll just cross it out. I'm going to use an annihilator. I have no idea how to spell annihilator. I'm not going to try. I will use an annihilator. I think it's A-N-N-I-H. If I try to do it on this thing, I just can't do it. I will use an annihilator. Okay, here we go. That looks promising. So what do I mean by an annihilator? I'm going to use an annihilator specifically for x e to the 2x. And by an annihilator, I mean a differential operator that annihilates this or sends it to 0. So you could think of this as being if a differential operator is a linear transformation from one vector space to another, then you could think about this as being in the kernel of whatever operator I'm going to come up with. So let's take the operator d minus 2. Okay, and we've already talked in the previous video about how d, so I'm going to call this operator a is d minus 2. So a of x e to the 2x is just this d minus 2 applied to x e to the 2x. And what do? I take the derivative and then I subtract 2 of the original function. And what do I get? I get, let's see, use the product rule, and I'm going to get e to the 2x. E to the 2x plus 2x e to the 2x, but then minus 2 times this whole thing, minus 2x e to the 2x. And I see actually this is not an annihilator. I lied. Okay, I was mistaken. These terms are going to cancel, and I'm just left with e to the 2x. Okay, so I have not annihilated this thing yet, but I'm actually close, because I at least got rid of the x part. So actually my annihilator is going to be d minus 2 squared. So ignore this for now. D minus 2 times e to the 2x is going to be, or times x e to the 2x will just give me e to the 2x. But then if I take d minus 2 squared and apply it to x e to the 2x, that's going to be just d minus 2 applied to e to the 2x, because if I apply it once, I get e to the 2x. I apply it a second time, we'll see what I get. Now I get 2e to the 2x minus, because I take the derivative, that's the d part, and then the minus 2 times the whole thing, and you see that that is 0. Okay, so d minus 2 squared is an annihilator, and we can talk a little bit about how I came up with that. I mean, that's sort of just something that you know that at some point you've seen this happen enough times that you know to look for that kind of thing. But since I have that annihilator, I want to somehow take advantage of it. So let's go back to this original equation, and if we know that we have an annihilator for x e to the 2x, how can we use that fact? Okay, so what I'm going to do is I'm going to apply that annihilator to both sides of the equation, if you will. Okay, so I get a times, and then we had d cubed minus 3d squared plus 4, and actually, yeah, we'll do this, times y, or applied to y, is equal to 0, because I annihilate the right-hand side. I know that if I apply a to what I had before, I'm going to get 0, so I just applied a to both sides. All right, well, that's d minus 2 squared times, and then I can actually factor this polynomial here. It's actually going to factor as d. It's not a polynomial, but I can sort of factor it like a polynomial. Again, we mentioned this in the previous video, that you can factor this like a polynomial, which is kind of a cool fact. So it's really d minus 2 squared times d minus 2 squared times d plus 1 applied to y equals 0. And this is actually a homogeneous differential equation. Because if I were to expand all this out, which you can do, again, you can treat these sort of like polynomials with factoring them and multiplying them, and you can kind of rigorously prove that it all works out. And it's not too hard. So you can expand all this out, and what you're going to get is a homogeneous linear differential equation, which we know basically how to solve those sorts of things. Okay, and you just find you find the roots of the corresponding polynomial, and you use those in your powers of e and so on. So let's think a little bit about why that's useful. Well, what we've said is that if y solves this equation, then y is also going to solve this equation. Now, the opposite is not necessarily true. Okay, so it's not going to be true that every y that solves this homogeneous equation will also solve this equation. I mean, take 0, for example. 0 solves any homogeneous equation. It certainly solves this last one. If you take some operator, apply it to 0, you're going to get 0. You apply some other operator to that, you're going to get 0. Okay, so 0 solves this, but does 0 solve this? No, of course not, because you would get 0, not x e to the 2x. So not everything that solves this homogeneous equation is necessarily going to solve the original thing we're looking for, but we do know that everything that solves the original thing we're looking for is, in fact, going to solve the homogeneous equation. And so it'll help us find all the solutions, and then some. Okay, so let's try to find, how do we find solutions to this homogeneous differential equation? Well, it's a fifth order linear differential equation. And so the existence and uniqueness theorem and some corollaries of that maybe allow us to say that if we can find 5 linearly independent solutions, then we can find all solutions. All the solutions would just be linear combinations of those. Okay, so it's a fifth order differential equation. If we can find 5 linearly independent solutions, then we're golden. I can rewrite this, by the way, as d minus 2 to the 4th times d plus 1 of y equals 0. And the characteristic polynomial, of course, is r minus 2 to the 4th times r plus 1. And we know that this d plus 1, or this r plus 1, well, I'll say this, d plus 1 gives us e to the negative x as a solution. Okay? And the reason for that is because d plus 1 annihilates e to the negative x. So if you think about what happens if you apply d plus 1 to e to the negative x, it's going to give you 0. Okay? So, so d plus 1 is going to give us e to the negative x as one possible solution. D minus 2, if you apply that to e to the 2x, it's going to annihilate e to the 2x, and so e to the 2x is also annihilated by this whole thing. But because we have not just d minus 2, but we actually have d minus 2 squared, that's an annihilator for not only e to the 2x, but it's also an annihilator for x e to the 2x. And then because we have d minus 2 cubed, that's going to annihilate, that's even going to annihilate x squared e to the 2x. And actually, we have one more power, it's d minus 2 to the 4th, and so that's going to annihilate as far as x cubed e to the 2x. And so the whole thing will annihilate all 5 of these functions, and these are all linearly independent. We've talked in previous lessons about how these are all linearly independent. Okay, so now we have 5 different solutions to the homogeneous equation. They're all linearly independent, and so because it's a 5th degree linear or a 5th order differential equation, we know that any solution, including any solutions to the original equation, remember any solution to the original is also a solution to this homogeneous, so any solution to the original will be a linear combination of these guys as well. Okay, now you might say, but wait a minute. Wait a minute. And if you're feeling a little bit uncomfortable, maybe that's a good thing. Hopefully you're uncomfortable for the reason I'm about to address, and not some other reason that I'm not going to address. Okay, so we know that d plus 1 annihilates e to the negative x. How do we know that this whole thing, d minus 2 to the 4th times d plus 1, that's a different operator? How do we know that would annihilate e to the negative x? So we know that d plus 1 applied to e to the negative x is 0. How do we know that d minus 2 to the 4th times d plus 1 applied to e to the negative x is 0? And here's the answer to that. It's a composition of linear operators, or you can at least think about it that way. You can think about it in a number of different ways. You could think about it as expanding all of this and doing it all at once, or you could think of it as first applying d plus 1, then applying d plus 2, and doing that 4 times. Okay, but if you did it that latter way, if you first apply d plus 1, you've got d plus 1 applied to e to the negative x. Here I'm going to put my little bracket there. That's going to be 0. And then you take d minus 2 to the 4th, and you apply it to all of that. You're going to end up with just a linear operator d minus 2 to the 4th applied to 0. So here, I haven't shown that it's 0 yet. It's d minus 2 to the 4th applied to 0. And what's the derivative of 0? 0. What's 2 times 0? 0. And you just keep doing 0, 0, 0, 0. And you're going to get 0. Any linear differential operator, when you apply it to 0, is just going to give you 0. Okay, so that's why if we know that this first one, and if we know that the first term annihilates a certain function like e to the negative x, then we know that the whole thing, and when I say first, I mean the one on the far right. But then you might say, all right, well, what about d minus 2, or even d minus 2 to the 4th? How do we know that even if d minus 2 to the 4th annihilates x cubed e to the 2x, how do we know that since it's on the left, it's not on the right? So by the time by the time we apply d plus 1 to whatever we have, we're going to end up with a whole different function. Okay, what about x cubed e to the 2x? And by the way, I haven't shown explicitly that this and that d minus 2 to the 4th annihilates x cubed e to the 2x. I'll probably do that in a future video, but for now, just trust me on it. It's not hard to check yourself either. It just takes a little bit of work, but it's not even that bad. Okay, so the question is d minus 2. You might say, okay, well maybe if I had d plus 1 times d minus 2 to the 4th, and you apply that to x cubed e to the 2x, maybe we can see why that's 0, as long as we accept that d minus 2 to the 4th annihilates this thing. Then that means that that if we think of it as a composition, then by the time we apply d plus 1, we're just applying d plus 1 to 0, and so of course we're going to get 0. Okay, so maybe as long as we accept that this annihilates that, then the whole thing should annihilate it. But does d minus 2 to the 4th, if we apply it second, if we first apply d plus 1, it's less clear immediately, at least. It's less clear that that should annihilate. Whoops, that should have been an e. E to the 2x, we'll say that. It's less clear that that should be 0. But here's the thing. Remember, I said you could just expand it, and the operator that you would get would be the same as the operator if you composed these. So if you were to expand this, the second thing, it would give you the same operator as if we were to expand the first thing. They work like polynomials that way. So they actually are commutative. You can do it in either order you want, and you're going to end up getting the same thing. Okay, so then that's why these are all solutions. These 5 functions that I have right here are all solutions to this homogeneous linear differential equation. Okay, but we also know that 3 of them, that these first 3, these are also solutions. The original homogeneous, maybe if we had a 0 right up at the top here, y triple prime minus 3y double prime plus 4y equals 0. So they also solve that original thing, the homogeneous part of that original plus 4y equals 0. And so any particular solution to the original equation, we should be able to write it as a linear combination of just these two. So the form that we're going to end up looking for is we're going to look for a particular solution of the form a times x squared e to the 2x plus b times x cubed e to the 2x. All right, so that's the kind of thing we're going to look for, and we end up finding that maybe I won't do it just to save time, but we can find that, and that's how the annihilator method works. So finding the annihilator, just to summarize, we were able to find an annihilator of x e to the 2x. That annihilator was d minus 2 squared. Then we apply it to the whole original differential equation. So this is the original differential equation. and we multiply, well, not really multiply, but apply the annihilator to that, and then we can sort of treat it as if we're multiplying polynomials, and then we have a homogeneous differential equation. We know how to find the solutions to that, and from there we can figure out which solutions will also solve the original homogeneous. We can kind of ignore those and then look for a particular solution of a specific form. So the annihilator method was what ended up letting us know that this was the right form to look for. Okay, so hopefully that was a good review of the annihilator method. I might do a video later about how to find annihilators of specific types of functions, but for now I'm going to stop here.